Thank you. Okay, thank you for the introduction. Oh, sorry. Okay, I'm Shuchen Lee, a PhD student at Yale, and today I'm going to present our work on the hardness of learning one hidden layer neural networks. This is a joint work with my advisors, Ilias, Zadik, and Manolis, Zampetakis. So we'll focus on one hidden layer neural networks. I guess you all know like what is a neural network, but depending on how you count numbers, this might be a 2 or even 3 layer. So let me clarify that. By one hidden layer, I mean one non-linear layer. So you get a neural network like this. And also you can write down your neural network as a function fx, which is a linear combination of k values, where k is just the width of your neural network. And let me denote this function class by this curly f and n with this subscript k, denoting the width k. And let me also formalize our learning model. So we will be considering the distribution-specific packet learning. So as standard packet learning, we have ID samples xi and y from the data distribution D. But for the distribution-specific setting, you have your covariate xi from a non-distribution dx, where we assume is standard normal. And you have your label yi to be f of xi plus xi, where f is the function you want to know inside of this function class you're learning. And you have a noise xi, which is also Gaussian, with variance sigma squared. And the goal is to find a hypothesis h with small loss. And here we'll be using the mean squared error. So how small do we want? In a weak learning setting, which is also the setting we're considering, we only need this hypothesis h to beat the trivial predictor by some edge epsilon. So the trivial predictor just output a constant, which is the mean of fxi, oblivious to the input given to the predictor. And you can think of this epsilon as an inverse polynomial in the input dimension D. So the question is, can we learn one hidden layer neural networks with Gaussian input in polynomial time? So the previous works on this problem is basically in 2 directions. The first is algorithmic results, and the second is the lower bounds. So for the existing algorithms, so basically the existing algorithms can be divided into 2 categories. The first is based on tensor decomposition. But the issue with that is it will need the way to be linearly independent to do tensor decomposition. So they cannot learn a too wide neural network. Like you cannot be, your width cannot larger than the input dimension D. And second is based on dimension reduction. And you only need your weight to be positive. But now your width is even narrower, like square root of log D. For lower bounds on this problem, previous works has shown that for neural networks with 3 and 2 hidden layers, this learning problem is hard based on some assumption from cryptography. And these hardness results even holds for the noiseless setting. In the previous works of Song, Zadik, and Bruna in 21, show that learning one hidden layer neural network is hard if the noise is adversarial with some bounded variance, like inverse polynomial. So our result basically improved their work from this adversarial noise to a fully random Gaussian noise. So let me formally state our result. So assuming CLWE, which I will explain in the next slides, then there's no polynomial time algorithm that can weakly learn this class of one hidden layer neural networks and, over the Gaussian input and Gaussian noise when the width is larger than roughly square root of D, and your standard deviation of the noise is roughly 1 over poly D. And one remark is that under some slightly stronger assumption, you can make your this sigma even smaller. Like you can make it subpolynomial, very close to e to the minus square root of d. And also by some simple padding argument, you can actually make your width to be any polynomial in D. So this is basically our result. And let me explain our assumption, continuous learning with arrows, or CLWE. This is also the starting point of our reduction. So CLWE is saying the following problem. You want to distinguish two distributions. The first one is a structured distribution, x and z. And the second one is a null distribution, x and y. So the structured distribution and the null distribution has the same marginal on the covariate x, which is just standard Gaussian. But the structured distribution, the label z, is equal to this noisy linear function on x mod 1. So you're only taking the fractional parts of this value. And this weight w is a uniform unit vector, and psi is again a Gaussian noise. And in the null distribution, your label y is just a uniform random variable from 0 and 1. So the result of Brunner, Regev, Stone, and Tang in 21 says that this problem CLWE is not solvable in polynomial time for some value of beta and gamma, roughly polynomial in D. Otherwise, it will solve some worst case lattice problem, and then the lattice space cryptography just breaks. So under this CLW assumption, our reduction is basically in two steps. The first is to reduce the CLW problem to learning periodic functions. So suppose you're given a function phi, which is Lipschitz and periodic. Then you define the following function class, which is phi of this linear term in x for all the unit w. And you can think of, for example, phi to be a cosine or sine, something like that, as long as it's periodic and Lipschitz. So the reduction we want is if you are given samples from CLWE, say you have the structured distribution, x and z pair, and then you want to use a learner for learning periodic functions to solve this CLWE problem. So first of all, by periodicity, if you apply this phi on z, then this model 1 actually doesn't matter because we said that phi is a periodic function. So you can see that this hardness of CLW already almost give you some hardness on learning periodic functions because if you look at this last term, phi of gamma times inner product of wx plus noise psi, then this is almost the same as the samples for learning periodic functions. The only difference is that, so for learning periodic functions, the learning sample will have this noise psi to be outside of this phi instead of inside of phi here. So to overcome this problem, we just inject an additional Gaussian noise psi 0 and add it to the add it outside of phi. And it turns out that we can prove that these two distributions are close in TV distance, so that it can fool the learner you can fool the learner for learning periodic functions. So this is the first step of our reduction. And if we know that learning periodic function is hard, then it basically only remains to construct a hard neural network that looks periodic. And it turns out that we can find a periodic function phi, and it can be and also we can construct a neural network that coincides with this phi over some bounded interval. So let me give you a figure here. So the blue line is the periodic function, like this sawtooth-shaped graph. And the yellow line is the neural network we constructed. And you can see that these two functions coincide over a bounded interval. If you can see clearly, it's -3 to 3. And of course, this is a one-dimensional, one-dimensional construction. So we just plug in this gamma times inner product of Wx, so to get a hard neural networks in D dimension. So to summarize, we show that assuming CLW is hard, then learning one hidden layer neural network is hard. If the input X is from a standard Gaussian, and the noise is also Gaussian, and the variance can be even a subpolynomial, like e to the negative square root of D, close to that. And the width K is also polynomial in D. And there are still some open questions. So the first one is, of course, can you make this width even smaller, like polylog of D? And second is, can we pose some assumption on the weight and still prove the hardness? Because like I have just mentioned, the previous works on this problem basically has some, like the algorithmic works on this problem has some assumption on the weights, for example, linear independence. But our construction of hard neural network actually have its weight matrix to be rank 1. So there's still a gap therein. And that's all of my presentation. Thank you for listening.
Questions?
Are you familiar with the work by Santosh Rampala and John Gomez on like SQ for randomly initialized neural networks?
Not really.
Okay.
But yeah, there are also some SQ bound this problem.
Right. So from what I remember, they also had like showed that. Well, they showed high SQ, which means that something like. I mean, isn't that also related to like learning with errors? Because I mean, hard SQ means like hard for noisy parity, which is a version of learning with errors. I just wanted to know if those are connected to this.
Yeah.
In
So
that
actually,
But hard for
yeah.
this would imply SQ lower bound. I don't think it will go the other way, right? Like if there's an SQ lower bound that doesn't imply hardness and the cryptographic function.
That's right. Yeah.
Yes. But by the way, here this work of 2 hidden layer neural networks also has a SQ lower bound, and also like this DKKZ paper here also has a SQ lower bound for learning one hidden layer neural network.
Thanks.
Other questions?
Hi, you mentioned that you need some stronger assumption than CLWE to get that even a smaller bound on sigma. So what's that?
So yeah. So the hardness of CLW is from some assumption on the hardness of worst case lattice problems. For example, it's like some worst case lattice problem cannot be solved with polynomial D approximation factor. But actually, the best algorithm so far is only a algorithm with exponential approximation factor. So if you assume that you cannot have a like super polynomial sub exponential approximation factor algorithm, then you can get this sigma.
Thank you.